Okay, welcome everyone to this new talk in the DEGA webinar series. So it's my pleasure to introduce Usman Khan, who's an expert in signal processing, stochastic systems, optimization, control, machine learning. So he works at the intersection of many different areas. So it's very exciting topic. He got his PhD in 2009 from Carnegie Mellon University. And then he was also a postdoc at the University of Pennsylvania, a visiting professor also at KTH in Sweden. And then in 2011, he moved to Tufts University as a visiting assistant professor, where he then also stayed the rest of his academic career. And it's nice to hear that in September of this year, he will officially start as a full professor there. So congratulations for that to Usman. He received several awards, paper awards, as well as personal awards. He's also very active within the IEEE Signal Processing Society. He's part of a number of technical committees, also an associate editor for several journals. He was also chief editor of proceedings of the IEEE, the special issue on optimization for data-driven learning and control. And it's also actually in that context that actually his talk today fits. So talk about data-driven optimization, but then more also on the distributed aspects, which relates then to our webinar series very well. So looking forward to the presentation. So go ahead, Usman.
Thanks, Geert. Thanks for the nice introduction. Thanks, Hoito and Verena, for organizing this and inviting me. So as Geert mentioned, the topic for today is distributed optimization. We consider it to be a bit like in parallel. You can just think of it as distributed machine learning, where problems are stochastic and non-convex in nature. And I'll try to relate, bring some context on how machine learning is viewed as stochastic non-convex optimization and how we propose what solutions we are proposing, etc. So before I start, I would like to acknowledge my students, NSF, National Science Foundation in the US, for funding our projects. But all of this work is heavily driven by my students, and I owe them a lot. So a quick overview. We have recently seen that data hold a significant potential in addressing many of the traditional problems, many of the recent modern problems. Image classification, medical diagnosis is something which is more traditional, where we are looking at data being used in political campaigns and advertisements and recommendation systems, etc. And traditionally, if we think about how do we learn from data, there is this architecture where we have a centralized location that can communicate to maybe servers that are directly communicate to servers that are holding data, or the server has all the data. And in this type of centralized scenario, we often have this challenge of how do we move data between entities, how do we communicate, and the computation required on the entire large data set could be too burdensome. On the other hand, we can think of these distributed learning architectures where there is no center at all. Think of it as a peer-to-peer ad hoc type of a network. We throw wireless sensor networks on a field, and they just build a network using their local communication, local neighbors, etc. And each node has some data. Could be a lot of data, could be less data, depending upon their capabilities. And we would like to learn from this data based upon this distributed architecture. So my talk today is mostly on this right side, distributed learning architecture, where we don't have a center, but there are parallels to the other story, which I'll try to create as we go along. So a quick case study. So this is a very simple experiment we did, a logistic regression 2-class problem, where we are trying to train a model with 10,000 images to distinguish between automobiles versus airplanes. And if I do it on a centralized machine, which has all these 10,000 images, then in order to reach 70% accuracy, it takes us about 113 seconds. It was done in MATLAB. And distributed, if I do distributed, by that I mean that I have 4 nodes, if I remember correctly, for this experiment. Each node has 2,500 images. And what is the computational advantage, or in terms of time? We noticed that the distributed model was trained so that it achieves test accuracy of 70% in 49 seconds. So this is a good starting point. Like we see that there is potential in developing distributed algorithms. But formally, like how do we formalize this comparison? Like if I want to quantify the rate at which distributed kind of outperform centralized, that can I provide any formal theoretical guarantees? Under what conditions these guarantees are attained? So for example, if I have a very well-connected network where nodes are tightly connected to each other and the topology is controllable, versus I have another network which is completely ad hoc. Think of a nearest neighbor graph on a geometric distribution of nodes, then which topology would enable these type of advantages? And so this is what we want to study. This is what the overarching goal for my research for this presentation will be. And in the end, I hope that I can convince you that there are some theoretical guarantees that we can establish under different topology and data regimes, etc. So moving on, before I delve into the actual technical content of the talk, I'll give some preliminaries. So we start with a very simple problem setup example. So think of recognizing 2 different images. So in this case, they are traffic signs. And I want to build a model, a classifier that if whenever I see a new image, then the classifier tells me whether it's image A or image B. So in this case, this is a stop sign and a yield sign. So let's build some mathematics around this problem. So input data would be, so this talk is on supervised learning. So all of these data points are labeled. Input data would be a feature. So feature can be extracted from any raw data point, but you can think of this feature as the entire image, and we call it theta. And the j just depends the number of the index of the image. And this is labeled, so it has a corresponding label y. And then, so then we hypothesize a model. So a model is a classifier or a linear hyperplane X that predicts a label hat for each image that it sees. So if you look at the top left figure here, you pick a model X. So X is the straight line in this 2D plane, but more generally for a high dimensional image, it's a hyperplane. And my rule is that every point that is above this red line is a star, and every point that is below the red line is a triangle. So how do I quantify? So we can see that when I start moving this hyperplane, when I go from red to green, then different points become stars and triangles. So I can say that I would like to pick a classifier X star that minimizes some loss, this misclassification loss, over the data set that I was given to me. So for instance, the red classifier here misclassifies 3 triangles and 3 stars, so its scores is 6. We can say it, and then the green classifier, the score is 7. So we want to pick red here because red is classifying 1 point better than the green. But this is just a raw count of how we are counting misclassifications. We would rather have a loss function, which I describe as L, that compares the true label yj with the predicted label yj hat across all my data points, and I want to minimize this over my model X. So this is a very general learning problem or a minimization problem, which I have provided in a machine learning context. So now I would like to think about minimizing functions, and I would like to keep this intuition in my head that these functions in a machine learning context represents a loss function, which I incur when I'm training a machine learning model in the supervised learning context. And in general, we have seen many different type of loss functions, in our academic electrical engineering or data scientist life. So for example, signal estimation, LQR type of problems, the loss functions we consider are quadratic. So which means this curly L would quantify the difference between yj and yj hat as yj minus yj hat whole square. And we know about convex losses. So when we think about classification or logistic regression type of problems, we have convex loss functions, which we can make strongly convex by adding, regularizer, for example, based on L2 norm. And we can think of minimizing functions that are non-convex, where these loss functions are not necessarily quadratic. And these non-convex loss functions we have seen, and especially predictors, and the predictors are also not linear. We have seen these type of functions appearing in neural networks, dictionary learning problems, reinforcement learning, etc. So we would like to minimize functions. These functions could be convex, strongly convex, or non-convex, depending upon the application that we are working on. And based upon which class of function I'm working on, we will have different guarantees of the algorithms that we can develop. So in this talk, my goal is to search for a stationary point x star. And the definition of this stationary point x star is that the gradient of the function that I would like to minimize, at that point x star, the gradient is 0. Now, if again, the function is quadratic, 0 gradient means something. If a function is strongly convex, it means something else. If a function is non-convex, it means something else. And I'll go over the exact description in a bit. And we assume, so we would like to develop first order methods. So first order means that first derivative of the cost function, so gradient. So of course, I'm assuming right now that the functions are differentiable. Potentially, we can extend this work to non-differentiable functions by using subgradients, generalized gradients, but we haven't really done that yet, but there is a path. And I would like to solve these minimization problems when these functions, when the parameters of these functions, which are these theta j's and the labels, true labels yj's, when these are distributed over a network of nodes, you can think of them as machines, devices, and robots. So some basic definitions. So what I meant, like in what context do I need differentiability? So I consider a function which is a multivariable function, maps RP to R, and we assume that this function always have a strictly non-trivial lower bound, and we assume that this function is L smooth, and L smooth basically means that the derivatives of this gradients of this functions are Lipschitz continuous. But more intuitively, we can just think of L smooth functions as functions that have a quadratic upper bound. So if you look at this figure, any function that has a quadratic upper bound at every point where the growth of this upper bound is controlled by this parameter, capital L, uppercase L, is what an L smooth function. And we assume that the functions are L smooth throughout the talk. When I talk about convex functions, this everybody would be very familiar with it, but you can define them as a function so that if you take any 2 points on the function, draw a straight line, and the function lives below this line, or a definition that we have used in analysis, which is often the definition which is often more useful in analysis is that a convex function lives above all of its tangents. So at every point, if I draw this tangent to the convex function, then it's always above these tangents. And strongly convex functions. So these would be functions that have a quadratic lower bound. So when I talk about smooth and strongly convex functions, these functions would have quadratic upper bound controlled by a parameter L, and mu strong convexity would mean that they have a quadratic lower bound controlled by a parameter mu. And the ratio between L and mu, L over mu, is what we call a condition number, which is always greater than equal to 1, because you can see L here, the upper bound parameter should be greater than the lower bound parameter. And these are the L, mu, are the parameters that will, keep coming up when we do our analysis, etc. So minimizing smooth functions. So these different type of functions that I described, I would like to minimize them. And as I said, the criteria of my minimization, at least for the purpose of this talk, is that we would like to find a stationary point. And the stationary point is a point where the gradient is 0. And as I said, for different function classes, this means something different. So for example, for non-convex functions, which is the outermost boundary in this figure. Stationary points could be either a minimum or a maximum or a saddle point. So these would be the points where the derivative or the gradient would be 0. For convex functions, what we know is that at a stationary point x star, the value of that function is the unique global minimum of that function. And for strongly convex function, we know that that value, the unique global minimum, is also achieved at a unique global minimizer x star. So it gives me, these characterizations kind of gives me some understanding of the point that I'm searching x star on what are the what properties those x stars would have when I'm trying to minimize different function classes, or when I'm trying to solve different machine learning problems. And because these points, so now a very simple technique or method which allows me to search for these stationary points. So a simple method that has been used for a long time, very well known, is gradient descent. So it's built on a simple observation. The observation is that if you look at a function, if you see its gradient, so you can see that on the left function, the gradient is increasing in the right direction because the function is increasing. So I can minimize the function if I move away from the gradient, or if I move in the direction of negative gradient. So a simple intuition would be that whatever pick a point on this function x old and move in the direction of the negative gradient at that point, we'll get x new. And if a function is strongly convex, we can guarantee with strict inequality, but in general, we will always have this property satisfied that the function value at x new cannot be greater than the function value at x old. So it's always kind of lower bounded. And based upon this intuition, we have this method that is called gradient descent algorithm. It just says that, you keep doing this, keep applying this map iteratively, start with the point x0, apply this map at x1, keep doing it. And alpha is a step size that that controls the length of the step that I want to take. So for example, if the function grows very fast, we can see that the gradient step is going to be too drastic, and we want to control that by choosing the step size. And gradient descent, so what are the guarantees, or how we learn that gradient descent is performing good or bad, or how do we quantify its performance? We basically have some performance metrics, and we have rates. So for non-convex function classes, the performance metric that we choose in order to quantify the performance of gradient descent is the norm of the gradient at xk. So remember that we want the gradient at this, we are searching for a point x star where the gradient is 0. And for non-convex functions, the metric that we choose to describe the performance of underlying algorithms is the norm of the gradient. And we know that gradient descent has 1 over square root of k guarantee is the rate at which this norm goes to 0, at which the gradient norm goes to 0. And this is non-stochastic, not accelerated. By accelerated, I mean typically momentum-based algorithms. For convex functions, the metric we choose is the difference between the function value at xk, which is the iterative gradient descent, and the global minimum fx star. And if you remember, for convex functions right here, the function value at x star is the unique global minimum. And we know that gradient descent converges at the rate of 1 over k for convex functions. And for strongly convex functions, remember, strongly convex functions are bounded below by a quadratic, and they have not only a unique function minimum, but also a unique function minimizer. So I try to depict it here. And we use the same metric potentially as the convex function. Sometimes we also use the norm between xk minus x star, because in this case, x star is unique. So this is a meaningful kind of an objective. And for strongly convex functions, we know that gradient descent converges exponentially. And typically in when we write papers, we often say gradient descent converges linearly for smooth and strongly convex functions, but that linear basically means that when we plot an exponential decay on a log scale, it looks like a straight line. So let's, after this, simple intuition behind gradient descent, how does this work? What do we expect from gradient descent under different function classes? We can think of just, a simple exercise. What happens if I do it on data when the data is distributed? So imagine I have, these 13 or some points, actually 18 points distributed over 4 nodes. So I have purple, blue, orange, and green nodes. And if every node implements its own gradient descent algorithm to learn the optimal, local optimal classifier, it will just find a line that fits its own local data. And in this case, you can see that orange and green regression lines would be nowhere close to the global truth, which is this black line. So we can see how potentially when the data is distributed, the learning based on local data could be completely, against the global truth. In this case, local gradient descent does not lead to agreement on the optimal solution. And typically for a distributed algorithm, when the data is distributed, we require agreement that every node agrees to the same solution and the solution they agree to is optimal. So distributed optimization, smooth and strongly convex problems with full gradient. So I'm currently restricting to a very small function class, which has smooth and strongly convex, so bounded above by a quadratic, bounded below by a quadratic, and a convex function. And I'm using full gradient, so which means there is nothing stochastic randomness. If the function is f, I have its gradient, gradient of f. Problem formulation, so I'll redefine my problem for distributed data scenarios. So I want to minimize a function capital F, uppercase F, when the function is a sum of local functions such that each local function lives on this communication graph. So F1, F2, generically called Fi, and I have a total of n such nodes. Each Fi is private to node I. So if you go back to my initial example, you will remember that this Fi in a machine learning context is actually a loss function, which is a function of our model, that how we predict a label based upon our features or images. So this function Fi is a function of all the local images that each node may have. And these images, the data that each node has, these images are private to node I. We assume that these functions are Li smooth and mu I strongly convex. So smooth and strongly convex, assume for now, we'll relax later. And the nodes in the network communicate over, the nodes communicate over a network, and the network is connected. So in this case, especially, you can see that we are not necessarily requiring this network to be undirected. So some edges have, just one direction, but as long as there is a path between every two nodes, that suffices for us to build algorithms. And of course, we know that we want to minimize the sum function. So I highlighted blue here, the sum, because we need to remember that we want to minimize the sum function, not the local Fi. And under these assumptions that they are Li smooth and mu I strongly convex, this minimizer x star will be unique and global. And at that point, we know that the first derivative or the gradient of this cap f function will be 0. So a very well-known algorithm to solve this distributed optimization problem is mix and descent. We call it distributed gradient descent. So we think of that as, so if you remember, if you ignore the red part of the equation here, you can see that this is just gradient descent implemented on local data, local gradient descent. But what this algorithm does is, after implementing, taking this first, it will ask, so node 1 here will ask nodes that it's connected to 2 and 4 for their models, so their classifiers. It will take some linear combination of those classifiers and then take a step in the direction of the local gradient. So it mixes first and then takes the step. The weight matrix has to have certain properties, that it has to sum to 1 on both rows and columns. So this is what we call doubly stochastic matrices. And the guarantee we have that this algorithm converges linearly up to a steady state error. So it will keep going down. So if you notice, this is a log scale. So the error keeps going down linearly on the log scale, so exponentially. on a regular scale, but then it has a flat steady state error. And this is when we choose a fixed step size alpha. And if we want this algorithm to converge to the global, to remove the steady state error to converge to the global X star, then that is possible, exact convergence, but we need to choose a decaying step size. And if we choose a decaying step size, then we lose the linear nature of the rate becomes sublinear. So if I plot, for a simple smooth and strongly convex problem, if we want to visualize gradient descent, which is centralized, which has all the data, because the functions are smooth and strongly convex on a log scale, the residual will go to 0 linearly. And distributed gradient descent, which is that mix and descent algorithm, will come down linearly but then settle at some error. So it begs the question that how do we remove the steady state error in distributed gradient descent? And here is our first contribution, and I'll give you context on what others have done also. So we want to minimize the sum function, right? So in other words, we want to search for, we are searching for a point X star such that the gradient of the sum function is 0. The problem with the distributed gradient descent is that with the constant step size alpha, X star, which is the gradient where the sum function is 0, is not a fixed point. So for example, if every node starts with X star, right, you can see that because the weights sum to 1, the first term here will be 1 times X star, so X star. But the second term is not going to be 0. It's not 0 because the gradient at X star is 0 only for the sum function, but not for the local functions. So that means that even if every point starts with X star, distributed gradient descent will not give us X star, so X star is not a fixed point. And we can fix this, and this problem, of course, so this problem comes from the issue that local cost, which is gradient at Fi, is different from the global cost, which is the sum gradient, or the gradient of capital F. So this, if we want to quantify, we call this parameter eta. So eta would be the difference between local and global cost. And a potential fix would be to replace this gradient with another variable y that tracks the global gradient. Okay, so imagine that instead of the local gradient here, delta f, I have a variable y, but y tracks the sum gradient. And this technique was introduced back in 2015 by the Scootery's group and Li Hua Shi's group in Singapore for undirected graphs. And in our work, we work on this technique on directed graphs. And this is how the solution looks like. So instead of taking a step in the direction of the local gradient, I'll take a step in the direction of y. And this variable y is updated as according to the second equation. So you have to here believe me that the second equation, as k goes to infinity, tracks the sum gradient. And of course, there is a way to show that. And in the first step, when I choose the weights on how I mix the incoming information, I choose these weights to be row stochastic in the first update, column stochastic in the second update. So this AB method that we proposed back in 2018 was when updates when the weights in the first are row stochastic, weights in the second are column stochastic. By then the work assumed both to be doubly stochastic. So there is a potential advantage of choosing row and column stochastic weights that are not necessarily doubly stochastic is that the algorithms are applicable to directed graphs. And we showed that many existing algorithms, which are known as push, decay, adopt, and frost, etc., are actually special cases of this update. And if you have seen work based on push sum, basically what push sum algorithms do is they can be interpreted as a special case of this algorithm AB by doing a state transformation in one of the two updates and adding a Perron vector learning type of a step. We can go into details, or I can point to the literature if you are interested. So the intuition should be straightforward. Like, I would just like you to remember that instead of taking a step in the direction of the local gradient, we'll take a step in the direction of a variable yk, which becomes the global gradient as the algorithm progresses. And we can show that AB converges linearly to the global truth X star by adding this gradient tracking step for smooth and strongly convex functions over both directed and undirected graphs. We have further added momentum to it. So you can add a heavy ball based polyax momentum here. You can add a Nesterov momentum here, and then we can show, at least in experiments, that the convergence is accelerated. And this is here a glossary of what the results we have so far. But we have developed results where the step sizes at each agent are not necessarily the same. There is work done by Shipu and Angelia Nedich over mean connected graphs. We have work on time varying random graphs. There is work by Gesualdo, Scuteri, etc. on non-convex problems, asynchronous problems. People have worked on delays, etc. But at least from my best knowledge, there are no explicit rates. For smooth and strongly convex problems, if you remember, kappa is the ratio between L and mu, which is the upper bound quadratic, lower bound quadratic. So gradient descent, we know that its dependence on the condition number is kappa. For the AB algorithm that I just showed you for directed graphs, we have kappa square. For undirected graph, we have kappa 5/4. I believe that both of these could be kappa as well, but this is a restriction of more analysis. We have seen in experiments that AB for both undirected and directed graphs behaves as kappa, but theoretically we can only show kappa square for directed. AB for directed graphs, if you want to add momentum, we can show linear convergence for a range of parameters, but this linear convergence means that the error decays linearly. Acceleration would be that it decays faster than the non-accelerated version, but that we have only seen experimentally, and there is no theoretical proof yet. AB for undirected graphs, there is the condition number dependence has been shown as 5/7 with Nesterov momentum, but for directed graphs, convergence and acceleration are both open. We have shown some numerically results numerically. And this is how all of this looks like in the end. So gradient descent is this black curve. So smooth and strongly convex problems converges linearly. Distributed gradient descent without gradient tracking has a steady state error. AB algorithm adds gradient tracking and gives me linear convergence again. And if I add momentum to AB, then it accelerates and becomes this, faster version of this blue, versus if I just add momentum to the plain vanilla gradient descent, it's that red curve. So addition of gradient tracking recovers linear convergence. Acceleration can be numerically shown, but it's not yet proved. What happens when the gradients are imperfect? So now when I implement the gradient in my algorithms, I'm assuming that I know the gradient perfectly. But if the gradients are only known in a stochastic sense, that there is a sample from the gradient distribution with variance mean zero and variance nu square, then you can see that these nice looking curves where gradient tracking converges linearly, gradient descent converges linearly, they're all lost, and I have, a steady state error. So for distributed algorithms, this magenta curve, there is a theoretical result that for stochastic gradient descent, the residual, the difference between the iterate of the algorithm xk and xk star in the mean squared sense converges linearly and then settle at a steady state error. And that steady state error is a function of the variance, so nu square, and eta. So if you remember, eta is that global versus local bias. And with the help of gradient tracking, so again, remember that there is no gradient tracking in this curve. With the help of gradient tracking, we can remove eta, but the variance is still going to be there. And lambda is a network parameter because remember, everything is distributed, so the graph parameters come into play. And kappa square is that dependence on the condition number of the problem. So distributed stochastic optimization, non-convex problems. So I'll just move to non-convex stochastic problems now. So we assume that we are in the same realm. We want to minimize a function, uppercase f, which is the sum of local functions. And we have two measurement models. So in the first measurement models, I'm going to assume that the data is online or streaming. So at every time of the algorithm, I just pick one sample, a noisy measurement, GI, of the local gradient, FI. Okay. So if I implement gradient descent, it's going to be xk plus 1 equals to xk minus alpha times GI, where G is a noisy version of the true gradient. And every time I'm just allowed one measurement, let's say, in the online case. And the other scenario is this offline or batch learning scenario, where I have all the data before I start my training algorithm. So you can think of this as a image classification problem where all images I already have on my machine. And in which case, the local cost, remember the local cost Fi will be a sum over all the local data points or local images that I have, and I have a total number of m sub I images. So streaming versus batch, online versus offline. So this is the measurement model. And something on the communication model. So we also want to look at two different type of topologies. One of them is what we call a data center mimicking topology, where we have control over the topology. So we can wire high performance computing machines together according to whatever topology we like. This is a data center scenario, so every machine may have a very large number of data points, and the number of nodes may be small. So this is what we also call a big data regime, where the number of samples per machine is much, much larger than the total number of machines. And on the other hand, we can think of an IoT type of an infrastructure, so Internet of Things, where the topology is ad hoc. So remember, you are installing wireless cameras in your house or in your office, and wherever you put a camera, it basically in an ad hoc fashion builds a network. We have battery constraints, so these devices could be battery powered. The data that each device has is going to be not necessarily too large, because these are devices that are in an Internet of Things type of setting. And in this case, the topology is not really under our control. The number of data samples they have is kind of small. Versus, so I wanted to kind of differentiate between something that we call a data center type topology or problem paradigm, or an IoT type problem paradigm. And we will show that, we have shown that different algorithms, different type of algorithms work better for different type of, measurement models and different type of communication models. So far, if I do a quick recap, we can see that gradient tracking eliminates eta. So eta is the difference between the local cost function and the sum cost function. And we can explicitly see that eta appears in the residual error, as I showed you before. And we want to quantify the performance with respect to improvement with respect to gradient tracking. So we have done that, and we want to find out ways of eliminating the steady state error due to variance. And what can we say about different function classes? So again, convex, strongly convex. We have done some work on the PL condition functions and general non-convex problems. So here I will just pick a slice of some algorithms that we have considered. And I want to motivate that this new framework for that we proposed a few years ago. So this is what we call gradient tracking plus variance reduction framework. So this is the problem. So each node I possesses a local batch of MI data samples. Think of them as images. So node 1 has images of all elephants, node 3 has all lions, node 2 has wolves and dogs, and node n has like a small number of images for every different problem class. Arbitrary data distribution. And we want to learn a classifier that can distinguish between all of these different labeled images. And the problem now is to minimize the sum over all nodes I. And at each node, because we have batch data, each node has a cost function that goes over its local data samples that are indexed by J. Okay, so we have two kind of sums going on. So you can imagine that if I build gradient descent based upon the local gradient, right? The local gradient in this case will be the gradient of this entire second sum over J. But that's going to be prohibitively expensive, because if I have 1 million images on my machine, I cannot compute all these gradients of high resolution images. So local gradient computation is expensive. And traditionally, the way we solve this problem, we would say each node I will do, the local distributed gradient descent type of a mixing step, and then take a step in the direction of one image, which is arbitrarily sampled from the basket of images that node I has. Okay, so this tau is basically a random number that is generated between all the number of images that node I has, and this will be a stochastic implementation of distributed gradient descent, where the performance will be impacted because of the variance that I incur due to the sampling process, and that even if I have the entire data here, then this data is far from the global data. And you can also, intuitively think about in this way that if node 1 has always seen elephants, then it probably has no idea how to distinguish what is a lion, right? So that's the local versus global data dissimilarity bias. So the framework has two steps: local variance reduction. So remember, we have a sampled gradient indexed by tau, which is a random number, that we implement in our estimator. That we implement in our algorithm, and then from that we want to build the entire local data and then the entire global data. So we want to build this type of a gradient. So what local variance reduction does, it's first samples and then estimates. So I have some variance reduction procedure that I will implement in order to go from my sampled gradient to a gradient that is an estimate of my entire local gradient. Okay, so this sum over gradient of fi is the sum over all j's. So I use my sampled gradient and I try to estimate my own batch. And then based upon what I have estimated, I mix with my neighbors in order to build, using gradient tracking, in order to build the global gradient. So these are the two steps. And there are different techniques that we can use for variance reduction here. When in centralized, people have proposed Saga, SVRG, Spider, and Sarah. And there are a few different methods of doing gradient tracking as well. What we have done so far are these three methods: gradient tracking with the Saga, SVRG, and Sarah based variance reduction methods. And all of these different methods have different kind of trade-offs, different regimes where one performs better versus the other, etc. So I will try to quickly go over gradient tracking plus Saga and perhaps SVRG if I have time. But this is what the variance reduction step in Saga works. So node I has 5 data points, or 5 images in this case. Node I at time 0 computes a gradient with respect to every image, right? And then in the next iteration, it will just update this gradient table with respect to just one randomly sampled image. So the first step, you compute gradient at every point, but then at every subsequent step, you basically just randomly compute the gradient at the new iterate at one random location. And then you update your AB algorithm, or the distributed gradient descent algorithm, based upon a simple average of this table, and you keep going. So this is what the GT Saga update is. And of course, we add gradient tracking, etc., to the mix. We have shown that for strongly convex problems, this technique converges linearly to the true solution without any steady state error. And we have shown linear speed up over centralized the counterparts, which is Saga, and network independent convergence rate for both non-convex problems and non-convex problems in the specialized Polyaglo-Yashevich type of class. The other technique is called GT Sara. So in this GT Sara method, what you do is every node I computes the full gradient, but periodically, right? So node I will compute at some time scale cap t. Node I will compute the full gradient, and then it will run for the next cap t steps with only local, one samples of the gradient. But after hitting this cap t again, it will recompute the global gradient. So you can immediately see that in the Saga case, I need storage, right? So if I have 1 million data points, I need to compute a gradient with respect to every data point and store them. In the second SARA case, which is a slight extension of SVRG, we don't need storage, but we require to compute full gradients after every periodic interval. So imagine that if I have 1000 gradient data points, and then I compute 1000 gradients here, I wait t steps, capital T steps, compute another 1000 gradients. But imagine if node R has 1 million data points, just for the sake of argument, then node R is computing 1 million gradients here, but my computation would be done much sooner, right? So I will compute 1000. I'm just going to wait for node R to finish its computation before the algorithm can proceed. So this second method, which requires periodic computation of full gradients, has issues with network synchrony, and the first method has issues with storage. So this is what in literature of distributed optimization we have kind of referred to as time versus space type of a trade-off. And we have, and again, space versus time trade-off, storage versus synchronizations. One method works for ad hoc networks where the number of data points are potentially small. So this is what I described as IoT regime. And in this regime, we have actually theoretically shown that GT Saga outperforms all existing methods. And in the second regime, which we call the big data regime, where we have controllable topology and potentially very large number of samples per machine, we have shown that the second architecture, which requires synchronization, it is actually optimal, as in that it meets the Oracle lower bound that is set for minimizing finite sum of non-convex functions. And these are the papers. If you are interested, you can go. Actually, both of these are published now. The second one is published in SIAM Journal Optimization. The first one is in Transactional Automatic Control. So quickly, I want to describe the results on GT gradient tracking plus SARA-based variance reduction, where for simplicity, we assume that each node has the same number of data points. In our paper, we have shown almost sure and mean square convergence for the GT SARA iterates. And again, if you recall, this is non-convex problem. So the metric we have is the norm of the sum gradient. So norm of the sum gradient in the limit as k goes to infinity is 0 almost surely. And we also have the mean square bound, mean square result. And if you look at this problem and ask this another parallel question, that what are the number of gradient computations required to reach an epsilon accurate solution when we want to minimize when each node has little m non-convex functions and I have n nodes. So we have this result, which in a certain regime that we call big data regime, as I described earlier, this complicated expression reduces to this curly h. Okay, so it's basically 1 over epsilon rate for the number of gradient computation requires to reach epsilon accurate solution. And this rate was shown to be optimal in the centralized cases, and our distributed algorithms in a particular regime that we call as a big data regime matches the centralized rate. We can see that this rate is independent of the variance. So nu square that appeared in the earlier analysis does not exist here because of the variance reduction. There is no eta, which I used before to describe local versus global dissimilarity bias. And there is no network effect here. So if you go back and you remember, there was this term 1 over 1 minus lambda, which kind of has computes or captures this the effect of the distributed communication graph. That is also not here. So what we have shown is that with the help of this SARA-based variance reduction and gradient tracking, these algorithms converge to almost surely to a stationary point, and the convergence rate does not depend on the network parameters in this particular regime or variance of the estimators. We can also show that GT SARA is n times faster than centralized SARA. So by that, what I mean is that the number of gradient computation required per node to reach this rate is 1 over n times less than the gradient computation required by the centralized method. So moving on, I have some performance curves which I can ignore for now, but we have results on large scale machine learning problems on these different type of regimes. We have effect of network topology. So basically, when I said that the algorithm is independent of the network, we can see that no matter what graph I chose, we have complete graph here. We have a directed exponential graph, a grid graph, a ring graph. The performance of the algorithm is kind of indistinguishable. And this is what we mean by a network independent performance. While in this case, we can see that in the IoT regime, the performance is not necessarily network independent. This is not something that we can show. So we have also results on online case. So remember, I told you about 2 different measurement models, online where the data comes streaming, and batch where the data exists in like a bucket. We have work on online problems as well that I have not described, but if you are interested, I can point in the right direction. And this is a quick demo, but this demo has nothing stochastic going on. But quickly, if I want to describe this, I have 100 nodes. Every node has 1 point in R2. And over these 100 points, you want to fit a line. So centralized gradient descent behaves like this. So this is the top middle curve, right? So the slope and intercept is just, centralized gradient descent is this dashed blue curve, which is fast. If I add on a distributed, if I don't do gradient tracking, then I have this curve. So remember, this pink curve used to settle with a steady state error. And when I add gradient tracking to it, I recover the steady state error and becomes this solid blue line. So you can see how many different estimates many different nodes start with their own estimates of the slope and intercept, and they kind of come together, agreement, and then they move together towards the optimal. So this is my last slide. There is a lot of work that is being done in this type of settings. Hoito here is an expert. Geert has done a lot of work. But if you are interested in learning more, we have an overview article on this gradient tracking plus variance reduction method, which appeared in Signal Processing magazine about 2 years ago. And we, as Geert mentioned in the beginning, we did the special issue for the proceedings of the IEEE, which has about, if I remember correctly, 12 or 13 articles by top people in this area of data-driven learning and control. So if you're interested, you can look at that and in order to learn more. But on this slide, I'll conclude, and I'll be happy to take questions.
Okay, thank you, Usman, for this very nice presentation and overview. Let's see, I see some questions in the chat, so maybe you can start there. So first question was related, yeah, you can also have a look. Is a clique pre-processing or something similar necessary? Otherwise, how do you decide which vertex is handling what function? So yeah, how do you connect functions to nodes? I guess maybe is that the what is a node represent?
So you can think of this node as let's say a robot or a wireless sensor network or a camera that we have mounted. And the function that this local node has is basically a function that is based on its local data, right? So each node I has a loss function that compares the loss between the prediction and the true label. And the prediction and the true label are basically based on the local data set that exists at the local node.
Mm.
Does this answer the question?
Yeah, so I guess so. Andreas should respond.
Yeah, if you have a follow-up question, you feel free to write it on the chat and we can.
So related to that, maybe I can follow up on that. So if you suppose you have, let's say, a cluster of different processors, would it also be useful to just split your data into different subsets and then assign different subsets to different clusters and then run your distributed algorithm?
Yeah, so I think when you are distributing data on your own to different clusters, then you have a choice of distributing the data in a homogeneous IID type of a way. So in that case, if the local distribution of the data points is similar to the global distribution, then you can actually show that gradient tracking does not help a lot, right? Gradient tracking helps when the data distribution is heterogeneous, which means that my data is completely different from your data, in which case, when I implement based on my gradient alone, I'm going to be completely lost. So I think when you have the opportunity to distribute data, you may be able to do a more just distribution, and that could enable choosing different type of algorithms.
Yeah, okay, clear. So then let's take one more through the chat. And so it's also fine to unmute yourself if you want, but so you don't necessarily have to put it in the chat, it's up to you. But let's continue in the chat. So yeah, connections, through connections maybe to federated learning, vulnerability, and data validation. Any comments or thoughts? So yeah, this is related to federated learning, I guess, right? Somehow.
So yeah, so federated learning is the paradigm where you have a centralized parameter server and a lot of worker nodes around it. So the topology is more like a star topology, and I, as the parameter server, would ask every node to compute their gradient and update the model, and then just give me back the model, right? So when I hear all these models back, then there is a policy on how I average these models that I get back. And in federated learning, again, there are these notions of IID data or non-IID data, which again mean that do we need gradient tracking or do we not need gradient tracking in some sense?
I don't hear you very well. I don't know if Usman hears you, but.
Hello?
Yes, this is better, yeah.
Okay. So Usman, the data sets may or may not be distributed. And how if you
I think it's better to write this question in the chat.
Yeah, we cannot, the audio is interrupted. So yeah, maybe it's better to write it down.
I have a quick question. This is Hamid. This is Hamid. Yeah, very nice talk, Usman. I just have a very quick question, just to be sure. Now, related to your results in the non-convex case, this is just you're shooting for a non-stationary point. Not, I'm sorry, for a stationary point rather, not a global optimum, correct?
No, stationary point. So these are first order stationary point satisfies that the gradient is 0, but we have not done the second order analysis.
Yeah, thank you.
Future work would be to quantify the second derivative at that point to find something more information about the stationary point, but that is, that is future work.
Thank you.
Yeah, thank you.
Okay, thank you. There's a question also: in computing a single image gradient rather than the full gradient, is there any benefit from either a larger than one image sample size or a non-uniform selection of the single image? So yeah, it's a bit related to what you just said.
So imagine if you have 1,000 images, then the schemes that we are working on, that what I described, would sample one image at every iteration of the algorithm. So one is not a hard constant. So you can pick, let's say, 10 images per iteration of the algorithm. So instead of doing single image sampling, you can do a mini batch sampling where so we have these results could be easily extended to a mini batch setting. And typically, because I think the basic argument is that the distribution of images will be are more close together, right? So many images are very similar. So if you implement full gradient, then you are perhaps doing more computation than needed because many images are close anyway. So that's why sampling or building algorithms based on a fewer number of images, they outperform in many practical cases methods that are based on full gradient, because a small number of images kind of represent your entire global set anyway, right? So that's the idea. But again, it depends on the image distribution.
Yeah. Okay, then there's one more question. So these algorithms you have described exchange the variable or the model between the nodes. Have you looked at algorithms which exchange only the local gradient, especially in the context of non-IID class distribution amongst the nodes?
Yeah, so particularly we have not considered methods where we exchange gradients. We have only considered methods where we have exchanged, the classifiers. I think fundamentally, you can argue that exchanging gradients reveal something about your data, so you may lose privacy. But I am not kind of for and against one method or the other. Like if exchanging gradients would help, then sure. We have
when you do gradient tracking, then you somehow also exchange gradients, right?
In gradient tracking, we again exchange this variable,
right.
Y, which is a function of your local gradients. But if I go back to that equation, the Y is a function of the difference between your local gradient at time k and k minus 1 here. Yeah. Right. So inferencing gradient I think this is a topic of research and further kind of investigation where suppose that you have an intruder who interrupts this communication and hijacks these Ys, then can the intruder build the function from this Y, right? And that function will have information regarding your data.
Yeah. Okay, Reza, I see you raised your hand, so you can unmute.
Yeah. Hi, Usman. Thank you for your nice presentation and your folks. Yeah, I would like to know about the difficulty of the analysis of non-convex and non-smooth optimization in subgradient methods. So did you do anything over non-smooth and non-convex optimization in this area?
Well, there is work on non-smooth problems, but I don't think that there is any work that uses gradient tracking. So there is work on distributed stochastic gradient descent, which is the plain version without gradient tracking. And so I know some work on non-smooth problems, I think by Shomu Kar at Carnegie Mellon. And there, when we don't have gradient tracking, especially for stochastic problems, typically you would not choose a constant step size. You would choose a decaying step size. So the theory then that is applicable becomes the stochastic approximation type of literature. So we do have some work where we have used analysis of smooth non-convex problems and decaying step size. So we have a paper in PSP, but for non-smooth problems, my group has not done anything, but there is some work with that is not gradient tracking, but something does exist.
But could they just show that the convergence to a stationary point, it was hold or not in their papers?
I think they can show convergence to stationary points, but those stationary points, because the functions are non-smooth, they are defined using generalized gradients.
Thank you very much.
If I remember correctly. Yeah.
Great, thank you. Any other questions from the audience? Maybe I can close with one last question. So how does this relate to all this work on ADMM and where you have consensus constraints and you solve the problem like that?
There is a parallel story where you can add agreement as a constraint. We have, there is one paper that I did with my, friend at Finland, Themis, who now has moved to Cyprus, where we have used, but yeah, there is that alternate formulation, but that adds agreement as a constraint and not as an kind of averaging right away. But I consider the two problems, as different formulations, but the solutions are similar. There is work on distributed ADMMs as well. I can, if you're interested, point to some papers. There is work on primal dual aspects as well, and especially for the primal dual formulations, there is some similarity between these methods, which are kind of very direct primal methods, versus the other that we have explored, but not like completely followed up on that.
But I guess it's harder to analyze those algorithms, I guess, right? So
Yeah.
Okay, thank you.
Yeah, I mean, thank you everyone for attending the talk. Thanks Geert again for the invitation and the organizers. If you have any questions, you just write me an email. I'll be happy to follow up on offline.
Thanks, sounds great. So thank you all for attending, and then we will see you next time. So.